Hello students, welcome back again. Today we are going to discuss some problems of exercise of chapter number 13. Yesterday we finished the exercise problem of chapter number 12. So as you know that in chapter number 13 we talked about integral domain and field, and therefore the question will be based on that only. There are so many questions, more than 70 or so. Let us see how much we can cover today. Sometimes it is difficult to talk about each and every question, so many questions are there. But let us see. Question number 1, it says that verify the examples 1 through 8 as claimed. So there are examples claiming that a particular ring is an integral domain. So that you can do. Okay, I think during the class we have discussed them. And similarly, in question number 2, they are saying that you need to verify which of the examples from chapter example 1 to 5 are fields. Okay, so these you can do. Of course, we have done it in the class itself. Third question is interesting. Of course, we talked about when we were discussing about the integral domain. It says that a commutative ring with cancellation property under multiplication has no zero divisor. A commutative ring with cancellation property has no zero divisor. Okay, that is it says that the cancellation implies that it has no zero divisor. And what else we need if for a ring to be an integral domain, that should be commutative, and as well as it should have unity. Okay, so we cannot say this is they are talking about the integral domain because they are not talking about commutative ring with unity. But still, if the ring is commutative, then they are saying that cancellation will hold. Okay, whether there is a unity or not. Fine. So that is cancellation property implies that at least one of A and B is 0 if AB is 0. Okay. So third, let us see. So we can assume that let us A be a non-zero element. Okay. And A times B equals to 0. So now we need to say that at least one of them is 0. Okay. So under multiplication, okay, cancellation has no zero divisor. Okay, fine. So we can write that AB equals to 0. So this implies that A times B equals to 0, and 0 we can write like A times 0. And because A is non-zero and cancellation property holds, therefore we can cancel A, and therefore we have B equals to 0. Okay. All right. We are using here cancellation property. Cancellation. We are using cancellation as it is given. Okay. So once the product of 2 is 0, so one of them is 0. So this is what we mean to say that it has no zero divisor. Okay. So next question, question number 4, list all zero divisors in Z20. Can you see a relationship between zero divisors of Z20 and the units of Z20? And the next question, question number 5, it is a general case of the question number 4 that so that every non-zero element in Zn is a unit or a zero divisor. In fact, we will see later on that every finite ring, every element is any element is either, if you're taking any element in a finite ring, it is either unit or a zero divisor. Okay. So this is a particular case, this is more general case, and then later on we will have a more general case to this question number 5, and we will see that what happens if it is not finite. Okay, so the hint will go like this for question number 4. Let what we need to find the units. Okay, units and zero divisors. Okay, so let us see. Let A be unit. Of course, then it has inverse and it should be non-zero. Okay, so this is non-zero and is a unit. Fine. So this means that this implies that Ax equals to 1. Okay, Ax equals to 1, and this belongs to Z20. And this implies that Ax is congruent to modulo 1 to modulo 20. Okay, and this implies that 20 divides Ax minus 1. All right, so this implies that Ax minus 1 equals to Ax minus 1 equals to some 20 times of y, like this. Okay, 20 times of minus y. Fine. All right. This implies that Ax minus, or we can write like Ax, okay, minus 20 equals to 1. You know that here y belongs to, y is some integer, y is some integer, and it means that a and y, a and 20 are relatively prime. All right, this means that the greatest common divisor of a and 20 is 1. That is, they are relatively prime. Okay, so if a is unit, then it should be relatively prime to 20. So it means to find out units of Z20, we need to find all those elements of Z20 which are relatively prime to 20. Okay, and this go in reverse order too, if and only if. Okay, fine. Understand?
Yes, sir.
Okay, so let us see about zero divisor, zero divisor, zero divisors. So let us assume that let A is non-zero. Okay, and uh, greatest common divisor of A and 20 is a D. Okay, and just now we have proved that if A is non-zero and it greatest common divisor with the 20 is 1, then it is going to be unit. Okay, and because it is going to be unit, then of course this is non-zero. Okay, so this should be some D and D should not be 1. Okay, otherwise A becomes what? A becomes zero divisor. Okay, so we are assuming that the greatest common divisor of A and 20 is D, and which is not 1. And because D is a divisor of A and 20, therefore we can write A equals to ds and 20 equals to some dt. Okay, for some S and T belongs to the set of integers. Okay, by divisibility criteria, we can write like this. And because we need to show that now A is a zero divisor, so we need to find some T, some number with which when we take the product of A, we are getting 0, and that element should not be 0. Okay, so now we claim, we claim what we claim, that T equals to 0. Okay, and T is not equals to 0. So that's what we need. Okay, so it means what? A is non-zero and T is non-zero, but their product is 0. It means that A is zero divisor. Fine. So we can consider A times T, and A times T equal to A is nothing but ds. So we can write ds, and then T we can write like this, T itself, okay, and because they are integers, so we can they commute, so we can write like dt times s, and dt is equals to 20 here. This is 20. This is 20. 20. So 20 times and s, because it's a multiple of 20, so this is going to be 0. Okay, this belongs to z20, and this is 80. Okay, this is 80. So this implies that 8 times t equals to 0. But now we need to show that t is non-zero. Okay, you know, and since dt here uh, as d is as d is not equals to 1, okay, and their product with t is 20, product of d and t is 20, fine, and it is not 1. So therefore, 20 cannot be divisible by t. It means that a t must be a non-identity. If t is non-identity, then and the product of these two is 20. It means if, it, for example, if in case d becomes 1, then of course t has to be 20 or a multiple of 20. Okay, so that this 20 in Z20 is 0, and this t will come also 0 in that case. Fine. So this should not be, if d is not 1, then 20 should not divide t. And so, and if it is not divide t is not, t doesn't divide t, in that case, what happened? What happened that t is non-zero because t is not going to be a multiple of t. Okay, t 20 multiple of 20. T is not going to be a multiple of 20. So t is non-zero, and this implies that A is zero divisor. Question number, okay, question number 5. It says that so that every non-zero element of Zn is a unit or a zero divisor. I think you can do because proof will be similar to this, huh? Hello.
Yes,
You
sir.
can,
बस 20 जगह n
yeah,
लिखना
you can take 0 is not k, and this belongs to Zn. Okay, and then you can take let greatest common divisor of k and n is 1. So in this case, you can prove that k is a unit. All right. Then you can prove that k is unit. Okay. All right. So you can prove this. And in case if greatest common divisor of k and n equals to d, and this is greater than 1, then of course k you can write s times d for some integer s belongs to z. Okay. Then you can write k and n by d, and this is nothing but s times d. Here k you can write s times d, and n by d, and this is dd get cancelled. So we have s times n, and this is, since this is a multiple of n, so this is going to be 0. Okay. So since here you see that k is non-zero, and also n by d is non-zero, and as we have discussed earlier in the last question. Okay. So this is this means what? This means k is a zero divisor. Okay, but you can write in better way. I'm just giving hint to you. Question number 6. Find a non-zero element in a ring that is neither a zero divisor or a unit. So any idea? Question number 6. Find a non-zero element in a ring that is neither zero, neither a zero divisor nor a unit. Okay. Hello.
Yes,
Can
sir.
you see here in I think no, 2z, no, non-zero element in zero divisor. You can talk about two set of integers you can take, huh? 2 belongs to Z, and of course Z is 2 is not unit, whether it is zero divisor or not. If you are writing 2 times some x equals to 0, what about x? Can x be anything except non-zero? Okay, hello. And this is
So x
0 in a
should
set of
0.
integer if and only if x is 0, na? So you cannot
Yes, sir.
find any x which is non-zero, and so that the product of 2 times 2 and x is 0. So this gives another example. You can take maybe x belongs to the set of polynomials with the rational coefficients. So this is also a polynomial x itself with the degree 1. Okay, and if you are taking this sum product, another polynomial such that the product is 0, so this polynomial should be 0. Okay, otherwise there is no possibility. All right, because x is non-zero. Question number 7. Let R be a finite commutative ring with unity. Prove that every non-zero element of R is either zero divisor or a unit. So how they are important, that zero divisors and units. Okay. Mm. So any element cannot be both, I think, in a finite commutative ring, as they are telling that either it is a unit or it is a uh, zero divisor. Okay. What happens if we drop the finite condition? I think in a finite condition, okay, finite, it means they are considering infinite case. In infinite case, this will work. No, these two examples will work because Z, the set of integer, is an infinite ring. Okay, in which we have 2. For example, 2 is a element which is neither unit nor a zero divisor. Okay. But in case of finite case, in case of finite commutative ring, the elements are either zero divisor or unit. Okay. And moreover, they are talking about non-zero element. So what about zero? Zero is zero is a zero divisor or unit? Do you have any idea? I'm just asking you. Zero element is zero divisor or unit? Can we put it in some category? Zero is
No, sir.
neither zero divisor nor unit. Okay, so zero is neither zero divisor or unit. Nothing. Okay, so in Z20, in the first here in the example number, I think 4, example number 4, what they are telling that can you see the relationship between zero divisors and Z20 and units of 20? So in fact, this is a finite ring. So elements of these will be either zero divisor or units. Okay, once you find zero divisor, so other elements will be units except zero divisors. All right. So once you compute zero divisors with this, you come to know what are what are zero divisors. You compute units, then automatically you will be knowing that what are zero divisors, and you can put zero divisors except zero element. Okay. So zero is neither zero divisor or nor unit. Question number 7. Um, so let us say let R be a, I think, finite commutative ring. Okay, finite commutative ring with unity 1. All right. So we need to take let U belongs to R, which is non-zero element, is not a zero divisor. Is not a zero divisor. Okay. So here assuming that U is a non-zero element is not a zero divisor. So what we need to prove? We need to prove that this is unit. Okay. Then we claim what we claim. We claim that U is unit. U is unit. Okay. All right. So we can for this we can show that U times prove that okay. Okay. U times R. U times R. This collection we can take U and R, where R belongs to the ring R, and we need to prove this. Okay, then I'm leaving it to you to prove this. U R equals to U R this set, and this is equals to R. Okay, and also because one belongs to R, this implies that one belong to U R, because you have proved that this equals to this. Okay, so it means what? One equals to U and some R0 for some R0 belongs to R. Okay, and since U is non-zero, okay, and we are able to get some R0 such that the product of U and R is 1. So it means what? U is unit. So once we are taking some element which is non-zero and is not a zero divisor, then it is becoming a unit. Fine. This you can prove. This thing, okay. Prove yourself. Next question number 8. Let A be a non-zero element belongs to commutative ring. Prove that A is a zero divisor if and only if A square 0 A square B equals to 0 for some B. Okay. If the question 0 is non-zero and belongs to R. Okay. So okay, let A is a zero divisor. A is a zero divisor. Okay. Then there exists a non-zero B such that A times B equals to 0. All right, by definition. And this implies that A times AB equals to A times 0. And this implies that A square B equals to 0 in the right hand side. Okay. Okay, fine. And conversely, if we conversely, if A square B equals to 0 for some B is non-zero, okay, then we need to prove that A is a zero divisor. So how you can prove? There may be two cases. If to prove that AB is a zero divisor, okay, AB equals to 0, of course A is non-zero. Okay, if AB equals to 0 and B is non-zero, then we are done. All right, then A becomes zero divisor. And if A square AB is a non-zero, AB is non-zero, then AB is non-zero, then this implies that A square B, okay, A square B, by assumption this equals to A times AB equals to, because A square B is 0, this by assumption, okay, and AB is non-zero, and this would imply that A equals to non-zero, because of course, sorry, here. So what we have, A is non-zero, so we are able to get an AB which is non-zero, such that their product is 0. This means what? This means A is zero divisor. Understand or what? Hello. Is it clear?
Yes, sir.
Next, question number 8 and 9, you can leave them. Question number, they are from direct products. Okay, you can leave there. Question number 11, D is integer, then prove that is integral domain. I'm leaving it to you. Exercise. Okay, do yourself. Question number 12. I will do one only. Maybe we can take 1/2. They are telling that you can express this in, or we need to give reasonable expression for these four expression in Z7. So 1/2 means 2 inverse, all right, and 2 inverse of 2 in Z7 is what? 4, na? Hello, as
So
2
4.
times 4. Yeah, 4 times 2 equals to 8, and this is under modulo 7 is unity. Okay, like this. Similarly, other things also you can do. No? Hello. For
Yes, sir.
example, -2/3 also you can see. So how you can write? You can write negative times of 2 and 1/3. That is negative times of 2 and into 3 inverse. So inverse of 3 in Z7 is what? Which number?
4.
4. I don't think so. 4 into 3. 12. 12 divided by 7 is not a unit. You know?
7.
5. Yeah, 5. You know, 2 times 5, and this is equals to -10, and -10 in Z7 will become, I think, 7. What we need to add? 4.
So
Okay,
14
this
is it.
becomes. Sorry.
So -10 plus 14, 4 आएगा.
4, na? Yes. So this 4. Okay, this is equivalent to 4. You know, 3 times 5, you know, this is 15, and 15 is 1 under modulo 7. Fine. So rest thing you can find it out. -7 and square root of 1 by square root of -3. Okay. Question number 13, give an example of a commutative ring with 0 divisors that is not in integral domain. Anyone of you?
So even numbers.
Even number, set of even number. Okay, it's 2z, na?
Yes,
Without
sir.
zero divisor and not an integral domain. Why it is not an integral domain?
सर इसमें 1 नहीं, यूनिटी नहीं होगी.
Very good. Please, you can note down 2 points for this. Yes, because in an integral domain, I think a few lectures back, I told you that how many elements, minimum elements is required for an integral domain. Na? So that there we have seen that at least there should be 2. Okay, so of course, unity and 0, at least these should be there. All right. Okay, so 2 is there, and then 14. Find 2 elements A and B in a ring such that A and B zero divisor. A plus B is non-zero, and A plus B is not a zero divisor. I think you can take Z6. Na? I don't know. 2 is this one non-zero. 3 is non-zero, but 2 times 3 is 0, na? 2 times 3 is 0. So they are zero divisors. But 2 plus 3 is 5, and this is non-zero. And you see that 5 times x equals to 0. If you are writing here, then of course you find any x which is non-zero such that their product is 0? Can you find non-zero x such that suppose this is star hole. No, so that's why this is not zero divisor. Question number 15. There is a hint. Okay. So one thing here, they are using a nilpotent. Okay. So A belongs to a ring R with unity, and suppose that A to the power n is 0 for some integer n, and such an element is called a nilpotent element. Okay. Okay. So so nilpotent element we are talking about. We say that an element is nilpotent if there exists n, okay, positive integer n such that a to the power n equals to 0. Fine. So this type of element is called nilpotent element. Okay. So they are telling that if element is nilpotent, then 1 minus a has multiplicative inverse. Okay. So if element become nilpotent, then it is easy to find the multiplicative inverse. So we have some formula. Of course, you can use this trick. Okay. So if 1 minus a is there, then you can take the product of 1 minus a with this, and then you can multiply them. You will finally getting 1. Is it okay? 1 minus a, and then you can write 1 plus a square and plus a to the power n minus 1, and then you can take product. So when you multiply with 1, you will be getting 1 plus a square plus dot plus a to the power n minus 1. And if you are multiplying with negative a, so you will be getting a square minus a cube and so on. And finally, you will be getting a to the power n. I think, yes, a to the power n. Okay. So here a square will go away. Similarly, other powers, I think a square. A is also there, na? A is missing. Okay, I forgot to write a. So here a is also there. So this will get cancelled. Everything will get cancelled up to a to the power n minus 1. No, this will get cancelled.
Yes,
And
1
this is
minus a to
0.
the power n बचेगा.
This is 0, na? Because this is nilpotent. So we are left with 1. So it means that this is multiplicative inverse of 1 minus a. Next question, 16. So that a nilpotent element of a commutative ring form a subring. So you need to show that, let us say, collection of all those elements of a ring such that a to the power n belongs to a to the power n equals to 0. All right. So you know that a to the power n equals to 0 because if you take 2 elements and b to the power m equals to 0, fine. So a minus b, and you can consider plus to the power m minus m plus n. Okay. And then you can show that this is equal to 0. Okay. Similarly, what else you need to prove? Once you prove that this equals to 0, you can use, that binomial expansion. Hello.
Yes, sir.
Yes, you can use binomial expansion. Similarly, what else we need? I think product, no?
Yes, sir.
Closeness of closeness. No, not associativity, but two things I think. Closure of difference and product should be close, no?
Yes, sir.
So what else we need? We can consider a b to the power n plus n, I think, yeah. So you can also prove that this is equals to 0. Of course, this is easy, na? You can do this. Question number 17. 0 is the only nilpotent element of an integral domain. Now in another, I think, okay, nilpotent element is of an integral domain. So 17th, in an integral domain, you know that the cancellation law holds, na? cancellation law holds, and also what we say that there is no zero divisor in integral domain. There is no
Yes.
zero divisor, है ना? So what we can say that a to the power n equals to 0 in any integral domain. We are talking about integral domain. Okay, so we need to say that 0 is the only possible case here. All right, and n is the smallest such positive integer. Okay, in case of nilpotent element. Okay, so we can write a times 0. This is equals to 0, and this is a to the power n, and we can write a times a to the power n minus 1. And you know that in integral domain cancellation law holds now. So you can cancel these two. You can cancel these two, and this would imply that 0 is equal to n minus a to the power n minus 1. But this is the smallest one, n. Here, of course, I don't know. They have not written, I think. But for some positive integer, so this should n should be smallest. Okay, this n should be smallest such positive integer. Okay, so therefore, because n is the smallest such positive integer, so this is a contradiction. Okay, so this is a contradiction. So it means what? That we assume that a is non-zero here. We have assumed that a belongs to R. Okay, and R is nothing but integral domain. Fine. So it means what? It means a has to be 0. This means a need to be 0. For non-zero case, we if this holds, then we can get n minus 1 for which this holds. Okay. So, but the thing is that we have taken is non-zero. All right. Another definition is here, idempotent. So idempotent elements are those elements for which a square is a. So this is the element-based property. All right. So if we can find some element which is square equals a, then we say that that element is an idempotent element. So they are defining it, and then they are telling that you need to prove that only idempotent elements of integral domain are 0 and 1. All right. So in case of integral domain, if we are taking a square is a equals to a, so we can write a square minus a equals to 0, and this implies that a minus 1 equals to 0. And because there is no zero divisor in integral domain, so this implies that either a is 0 or a equals to 1. Fine.
1.
And then next question, question number 19, let A be idempotent or in a commutative ring. Idempotent and is a commutative ring. So that each of the following is an idempotent. I will show one, and the rest you can do if you want. So I need to show that they are idempotent. So AB square we need to consider. And this AB square, how we can write? Because it is commutative, so we can write AB and AB, and then we can swap these two. You know that in a group you have read already. So this is equals to a square b square. All right, and because this is they are idempotent, so a square is a and b square is b. So this implies that a b square equals to ab. So ab is idempotent. All right, so their product is idempotent. If there are two idempotent elements in a ring, in a commutative ring, then their product is going to be an idempotent element. This kind of thing is also going to be an idempotent element. They are all idempotent elements. In 20th question, so that in Zn, so that Zn has a non-zero potent element if and only if n is divisible by the square of some prime. You can try it, or if you are not getting solution, I will tell you. Okay, fine. So do yourself. Next question number 21. Also, you can they are asking about a continuous function. So you can so that R has zero divisor. They are asking that if R is a ring with the real ring of real valued continuous function on this interval, and then we need to show that R has zero divisors. It means that a non-zero function, product of non-zero function is going to be a zero function. So we can define it as x on 0 here in -1 to 0. Okay, and of course you can close it and then like this 0 to 1. All right. And then we can take another function g. They are continuous. You see that at 0 it is a break, but at 0 it is x becomes 0, so it is continuous. Here also let us define in other way. Put 0 here and x here, and you can take it same interval like this. Okay, and here 0 and 1. Okay, now you can see that the product of f and g in this interval is 0. F and g in this interval is also 0. All right, and none of them is 0 identically. No? None of them is identically 0. Identically 0 means all time 0. Okay. So next question number 22, prove that if a ring A is, prove that if A is a ring idempotent, then a to the power n. Okay. So they are telling that if A is square A implies a to the power n equals to a. Very interesting result, no? Very interesting. If A is a ring idempotent, then we need to prove this. You can use principle of mathematical induction. Principle of mathematical induction. Okay. For n equals to 2, a to the power n equals to a is true. Okay. And then you can assume that for n equals to k, and then for n equals to k plus 1, you can derive. I think you can do this, huh? And question number 24, 25 also, you need to find zero divisors and idempotent element. You can find it out. Question number 26, you need not to attempt. Question number 27. 27, it says that determine all elements of a ring that are both units and idempotent. Both units and idempotent. So it is unit plus idempotent. Idempotent means what? Idempotent means a square equals to a, and unit means a inverse exists. No, a inverse exists. Okay, so for this a is square a, this implies that we can write a minus 1 equals to 0. So this means, okay, because a is unit, so it is non-zero. Okay, so a has to be 1, and only possibility. Okay, yes. Only possibility is 1. 28th question. I think 28th R is a set of real function defined for all real numbers under addition and multiplication. It reminds zero divisors. So they are asking some small things that you need to find zero divisors, nilpotent element. Okay, so that every non-zero element of zero divisor unit or a zero divisor or a unit. Okay. So you can do these examples. 28th, 29 subfield test also. Okay, difference. The similar test is there. A difference should be in that set, and instead of product, there should be this kind of thing. Okay, and this you need to prove that this is a field. So I'm leaving them you to prove. Question number 31, R is a ring with unity if product of any two pair of non-zero element of R is non-zero, prove that AB implies. Okay. So R is a ring with unity. Product of any pair of non-zero element is non-zero. Okay. So A and B both are non-zero. Both are non-zero. And product also is non-zero. ये imply कर रहा है ऐसा. ठीक है. So हमें prove करना है कि AB अगर 1 हुआ तो BA भी 1 हो जाएगा. All right. So AB equals to 1. This implies that we can write A here, and then no. Okay, A B, and we can write in the right A like this. So 1 times A here. So this is A. Next, I think we can write A B and A. Okay, minus A equals to 0. And then this implies that we can take A common. So BA minus 1 equals to 0. You know? All right. So A is non-zero. So it means what? It means BA has to be
equal to 1.
B equals to 1. You know? B equals to 1. This we are using this thing. Huh? This thing because the product of non-zero is non-zero. So if it is becoming 0, it means something, at least one of them has to be 0. 32 question under multiplication and addition modulo 10. Prove that R is a field. You can try it. 32nd question. Okay, I think we don't have much time now. So let us conclude the discussion for today.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.